So in this portion, or in this video, we're going to talk about the rock portion of the carbon cycle, or a lot of people call it the carbon thermostat. So it has to do with ultimately regulating the amount of carbon dioxide in the atmosphere by changing the weathering rate. So we'll talk about, this is a little bit unfamiliar, so we'll talk about it a little bit here, and then we'll talk about it again in class. So the rock cycle is really governed by this weathering equilibrium equation that I'm showing you right here, which has igneous rock. So this is igneous rock right here. This is the kind of rock that comes out of volcanoes. And CO2, the gas, so it also comes out of volcanoes. And these two things combine, or can combine, if the conditions are right, to form CaCO3 or limestone through weathering. So this happens when carbon dioxide combines with water. So carbon dioxide plus water in raindrops makes carbonic acid. I don't know why I started that with a C. So that's H2CO3, carbonic acid. And that weathers igneous rock and forms limestone and silica, or quartz. All right. So this is the general equilibrium equation, and because CO2 is a gas, this equilibrium is really strongly determined by temperature. So if temperature and actually pressure are very high, this whole equation wants to shift this way. So the carbon dioxide wants to be a gas, and we end up with carbon dioxide and igneous rock. So that's like underground where it's very hot, there's a lot of high pressure, everything ends up going back into CO2 and igneous rock. Meanwhile, on the surface of the Earth, where temperatures are relatively low and pressure is relatively low, and that favors this direction. So when we're out on the surface of the Earth, carbon dioxide wants to combine with calcium to make limestone. And we end up with limestone and silica and less CO2 in gaseous form. So if we were to draw a picture of this, what might that look like? And you all know I have excellent drawing skills, so here I will, draw a volcano. Here is my rendering of a volcano, and a slope down to a subduction zone, which is usually right on the edge of the continental shelf. So here we're in the ocean, and here's the subduction zone right in here. Okay, so we have carbon dioxide coming out of volcanoes at a rate of, as we talked about earlier, 0.1 gigatons of carbon per year. And it combines with water to form carbonic acid, which then weathers igneous rock, so that carbon turns into calcium carbonate. It washes down slopes and into subduction zones, ultimately, where it gets buried and incorporated back into the crust, and this matches the degassing rate. This is about 0.1 gigatons per year again. And now it's back in these high temperature, high pressure environments, so it turns back into carbon dioxide and the igneous rock. Where it gets to come out as carbon dioxide again. All right, so that is kind of a little rendering of the rock cycle. And the next thing we're going to talk about is how the degassing rate really sets the amount of carbon dioxide in the atmosphere. Okay, so the rate of weathering really depends on carbon dioxide. It also depends on rainfall and temperature, but because rainfall is a function of temperature, and temperature is a function of carbon dioxide, it's really the carbon dioxide that sets sort of the rate of weathering overall. Here, the carbon dioxide is really what we focus on. So think about it in a couple different ways. First, I'll kind of draw a negative feedback loop like we were just doing in class the other day. If you have a lot of carbon dioxide in the atmosphere, then this means that the rate of weathering will be very high. So if you remember from the equation, this means that the rate of weathering is high. So a lot of carbon dioxide is coming out of the atmosphere and forming calcium carbonate, limestone. So that's taking carbon dioxide out of the atmosphere. So you're reducing carbon dioxide in the atmosphere. And then that in turn reduces the weathering rate. Until it matches the degassing rate. Okay. So another scenario may be that you have too little carbon dioxide in the atmosphere. In this case, because there's not enough carbon dioxide in the atmosphere to really promote weathering, this reduces the weathering rate. Which then lets carbon dioxide build up in the atmosphere. So this increases CO2 in the atmosphere until the weathering rate increases to match degassing. Okay, so that's kind of one way of looking at it. Another way is to draw this sort of thermostat-like picture where we've got carbon flux on the y-axis. That's kind of messy. And we've got a flux rate that's set by degassing, so this is the degassing rate. Here, it's a flux rate, so it has a one steady degassing rate. We're assuming it's not going to change over time. So if you start out with a whole lot of CO2 up here, you're going to have a lot of carbon dioxide in the atmosphere. So that means that your weathering rate is going to be very high. And as the amount of carbon dioxide in the atmosphere drops, because that weathering rate is so high, the amount of carbon dioxide will drop and the weathering rate will drop until it matches the degassing rate. Okay. Alternatively, you could end up with perhaps not enough carbon dioxide in the atmosphere. And in this case, the low amount of carbon dioxide in the atmosphere would mean that the weathering rate would be very low and low enough to allow carbon dioxide to build up in the atmosphere, which would slowly increase the weathering rate until it again matches the degassing rate. So it's sort of a stabilizing effect that brings about enough carbon dioxide in the atmosphere to give a weathering rate that matches the degassing rate. Okay, so we'll talk a little bit more about this in class. And then so on geologic timescales, so it might step back for a moment. It might seem that this weathering rate feedback between the amount of carbon dioxide in the atmosphere reducing or increasing the weathering rate so that the amount of carbon dioxide in the atmosphere is ultimately reduced so that the weathering rate matches the degassing rate. It's a negative feedback. Okay, which I just told you the answer to this question. But so it might seem like that's a good thing. It's going to help us out. It's ultimately going to take that carbon dioxide out of the atmosphere. But the problem is that it takes a really, really long time to do this. We're talking about a time scale of millions of years, million years. And that's something that we'll kind of grapple with when we look at this geocarb model in class on Tuesday. Okay, so the take-home points are that rocks, they're a really big pool of carbon with an incredibly slow turnover rate, very slow, so that ultimately this flux will take the carbon dioxide out of the atmosphere that we put in there into it, but it'll take a million years to do it. Okay, so on geologic timescales, the amount of atmospheric carbon dioxide in the atmosphere is set by the degassing rate. So that weathering and burial will eventually clean up our mess. It's just going to take a really long time. Okay, so the last video is going to talk about some of the other pools. We'll talk about the energy-carbon connection and carbon cycling on land, and then that will be it for the videos. So thanks for watching.